I've been asked to introduce my colleague, and I will do so. Chen-Fu Chiang joined the Computer Science Department in fall 2015. Prior to joining SUNY Poly, he taught at the University of Central Missouri, received a first bachelor's degree from National Taiwan University, further obtained a master's degree in science and engineering from the University of Pennsylvania, PhD in computer science from the University of Central Florida. After obtaining his PhD, Chen-Fu spent 2 years in Quebec working as a postdoctoral researcher at the Université de Sherbrooke. His teaching interests include algorithms, matrix linear algebra, database systems, and motivating students to be more self-driven. Primary research interests are in the field of theoretical computation, algorithm design and analysis, especially quantum computing and quantum algorithms. He's been working on understanding and demonstrating how quantum phenomena can be harnessed in order to dramatically advance the fundamental capabilities of information processing. And he will be presenting today on quantum algorithm. Pleasure, Chen.
It's a Friday and the weather is nice outside, so being willing to come here to listen to the lectures. Okay, so before I start, I should give you an overview of what I have done in the past, and the purpose of doing so is that just in case if any one of you find out something I did in the past have something to do with what you are doing now, and you are willing or interested in working together on something together, that would be very good. So this is what I did when I was a student. So basically, I studied the quantum walk. And I studied how to implement the quantum walk using the quantum circuit. And I talked about the heating time of the quantum walk. And then another thing I studied is the phase estimation. Phase estimation is a technique that's extensively used in quantum algorithms. So I was studying how to implement the phase estimation more efficiently, given certain constraints that these days we know we only have very few quantum bits, and the precision of the quantum gates are really limited. How do we implement the phase estimation efficiently? And that's what I studied over there. And with respect to the applications, I work on preparing the thermal gift states, and this is something that I've done a lot in physics. So, and I also study how to prepare or estimate the partition function. And here I sort of mark how the technique are used inside. But anyway, so if any of this are of interest to you, you're welcome. We'll be happy to work with you on this. So let us go back to the main topic that I want to talk about here. Today, the talk will have 3 parts, and that was the first one is why do you want to use quantum algorithms? Why will appear, right? Will appear because it gives you the promises of speed up. And this, I'll talk about the earlier quantum algorithm. And then I'll talk about more than 10 years old algorithms, like the quantum walk, and which has been used extensively. And the last would be something I've been reading recently, and I try to improve on it, is using the spectral probing approach to address the set problem. Set is the satisfiability problem. Okay, so part 1, the quantum algorithm. The first one is we're going to talk about what the qubits are and those earlier algorithms and the exponential speedup. So here, in order to understand the speedup, you probably need to know the following, the basics. So first of all, what's a quantum bit and what's a superposition? And what's a quantum circuit and how do you do the data manipulation? And then we talk about simple Deutsch algorithm, Deutsch-Jozsa algorithm. Okay, so what's quantum computing? So let's say Feng. So what's a quantum computing? So
is a quantum mechanics. Quantum mechanics
to solve problems, right? So you use all the properties try to build a machine that can use a quantum mechanical property to solve some problems. So a quantum computer is a machine that performs calculation based on the laws of quantum mechanics, which is the behavior of particles at the subatomic level. And what's a quantum computing? Quantum computing is that you use those mechanical properties in order to build a quantum computer and an algorithm such that you have a better performance in comparison to current computer technology. So that would be the goal of the quantum computer. Okay, so before I move on, I assume you have the following knowledge, right? You know what the gates, the wire, and you have some foundation in linear algebra such as matrix operation, tensor product, and the vector space. So I'm sure this is kind of the fundamental for most of us. So first of all, what's a quantum bit? So the quantum bit is a data that can be implemented physically by using two energy level of an atom. So you have an atom, you could have a ground state or excited state. And these are the candidates for quantum bits. So out there, maybe people have the quantum dots, they have photons, and they have all kinds of candidates to do this. So for us, we are the nano science, so they probably have a superconducting qubit or something like that, but I don't know much about that theory yet. So as you can see, so here there are many candidates for quantum bit. But the fundamental idea is that you have an excited state and the ground state. Okay, so let's turn that into the mathematical format. So we can simply represent a quantum bit in terms of that here the 0 means the ground state and the 1 means the excited state. So for any quantum bit, that can be expressed as a linear combination of ground state or excited state. The property is that the amplitude squared sum up to 1. So that's the law of the quantum mechanics. And the next thing we need to know about is the Hadamard transform. So Hadamard transform is the gate that used a lot in many quantum algorithms, because through the Hadamard gate you can prepare superposition. And superposition is the advantage in terms of solving many hard problems, because it's like a parallel computing. You have prepared all the states at once and you ask at the same time. Okay, so as you can see, here we have the right? So I'm going to write, this looks fundamental, but I'm going to write out the property because we're going to use them later in the second half, the first part. So you have Hadamard gate, the act on the 0 bit, then you have the square root half of the 0 and 1. And you Hadamard act on the excited state, you're going to have this superposition with the change in the coefficient. Okay. And then if you have edge acting on 0, you go back to 0 itself. Edge acting on 1, go back to 1 itself. Okay. So as you can see, if you just do it by hand with the matrix multiplication, then you can get this result quite straightforwardly. Okay, so now let us directly jump into some problem. So let's say here's a Deutsch problem. So if you are given the Laplace function, that's f. F maps the input 0 or 1 into 0 or 1. So the question is determine whether this function is constant or balanced. Right? Okay, so what does that mean? So what's a balanced function? Balanced function, for instance, if you have an input 0, 1, you use the function f to, then you get a result 0 or 1 to 1 or 0. That means 50% of the input goes to 0, 50% of the input goes to 1. That's so-called a balanced function. And what's a constant function? You don't care what your input is, directly you just map to a constant. Right? So that's a constant function. So now, simple question, how many queries, how many times you need to call this oracle, function f, classically in order to determine that this function is constant or balanced? 2, right? If you ask 1, you don't know. You got a number, you don't know. If you ask twice, definitely you know. Okay, of course, 2. Quantity you only need 1, but this is no big deal. I'll just go through the detail and then.
Subtract that,
Huh?
you can subtract.
What do you mean they can subtract?
I mean, if you subtract the values, you get always 0 with the constant. Oh, you still get two queries.
Yeah. So,
Yeah, okay, yeah.
Okay. So no matter what you do classically, you have to summon the oracle twice. But quantally, you just need 1. So here is our circuit. So here's the assumption that the oracle is expensive, and quantally, let's say you have a corresponding oracle. It's called UF. It has the following property: that this is your input X, and this is let's say scratch paper. You put the result out there. So if you're acting on X, then you dump the result of f of X into this scratch paper and solve them. This is a solve operator, right? Okay. So what does this mean? So if f of X is 0, so what happened to the scratch paper? Is Y solve 0. Anything solve 0 just itself, right? And if f of X is equal to 1, and Y solve 1 becomes the Y implement. So if Y is 0 at this moment, you become 1. If Y is 1, you become a 0, right? Okay, so let's look at, okay, so obviously, if you look at this guy, so UF is acting on the let's say this is your X, right? You don't know if it's 0 or 1, but let's say it's X. And then here you have the 0, 1 in the second register. And turn out the result is like this. Why? Because if f of X, so if your f of X is equal to 0, what's going to happen? Here, you're still going to change anything, still 0 minus 1, right? But if f of X is equal to 1, then what is going to happen? This guy will get flipped. This guy will get flipped. You got 1 minus 0. So obviously, the only difference is you just factor out what this f1 to the power of f of X is. Then you are done with this. You can simplify this computation here, right? Is that clear to you? Because if f of X is 0, so 0, then you are doing nothing, right? So you're doing nothing to this guy. So it's minus 1 to the power 0, which is 1, so 0 minus 1. Nothing changed. But if f of X is equal to 1, you have to flip it. So if you flip this guy, it become 1 minus 0. So which you have a negative sign, which is you can express as minus 1 to the power of 1, which is f of X question.
So in the bottom line there, UF, is there supposed to be a comma in there? We're operating on
Okay,
pairs.
so
The comma goes after the X or after the 0? After the X, right?
where this one?
Yeah.
No, there is no comma.
These are two. Okay, so this is the first qubit. This is the second qubit.
Okay, so there's a comma after the first qubit.
Okay, so normally they just ignore this tensor
okay.
product. They just
Yeah.
wrote it like so.
Okay, I
So
got
yeah, John, your question is, so actually I should just written that it should be X, and then you have, so you have another state. Unfortunately, this
Okay.
state is like this.
I got it.
Okay, so 0, minus 1, something like this. Okay, so is that clear now?
Yeah.
Okay, so obviously this is a property you can use, right? So now let us look at the simulation. So in the first step, alpha size 0, you have 0, not a problem. You have the 0 minus 1 divided by square root of 2. No biggie, right? So then you do the Hadamard. Hadamard, when you add up a 0, you have a 0 plus 1, right? Okay, you have a 0 plus 1, you use the Hadamard, so that will get a psi 1. So obviously psi 1 will have this state with this state. Is that clear? Okay, so what's going to happen if you use UF? So remember, that's what I just explained to you, right? So UF add on X 0 minus 1, you just say minus 1 f of X, X 0 minus 1. So here, this is your X. But here your S can be written in two parts, 0 and 1, right? So obviously here, this is the first part of X, and hooked up with this 0, minus 1. So you have minus 1 f of 0 associated with this, and minus 1 f of 1 associated with this, by simply using the property here. Right? Okay, so if you clean that a little bit, you factor out the f of minus 1 to the power of f of 0, you can rewrite this expression as this. And then if you are a very sharp observer, can you tell me, so what is this number? What happens if this number is 0? What are you going to get in this parenthesis? If it is SOR, let's say 1 SOR 1, or 0 SOR 0 is 0. So what are you going to get here? 0 plus 1. If you have a 1 SOR 0, then definitely here's a 1. So definitely have 0 minus 1. So think about this. If a 0 minus 1, which is this case here, right? This case here, you do another hadama, what you gonna get? 1 back. But if it's this guy is 0 plus 1 will be here. You do another hadama, you get a 0 back, right? So as you can see, if you apply another hadama, at the end of the day, you definitely gonna get back the result of this. So what does this mean exactly? So that means if f of 1 SOR f of 0 is 0, then you get this guy back, right? If f of 1 SOR f of 0 is 1, then you get 1 back, right? So what does it mean here? If f1 SOR f0 is equal to 1, so what does that mean about this function? It's constant or balanced?
It's balanced.
It's balanced. So if it's a 0, then it's a constant function. So obviously, you just ask the opera once by measuring the result here, then you get then you immediately know it's a constant function or it's a balanced function. So you say, no big deal, because this is just 2 query versus 1 query. I don't see any interest. So now, let's make it more interesting. Is that clear so far to everyone? Okay, so now, let's make your life a little more miserable. Okay, so let's say, now we have another block box. So here, your input is 0, 1 to the power n. So that means you have a 2 to the n inputs, right? And you can map them to 0 or 1. Okay, so now, once again, I define this function could be either constant or it could be balanced. So if it's a constant, that means everything mapped to the constant. If it's a balance, half of them mapped to one value, the other one mapped to, okay, half of them mapped to 0, half of them mapped to 1. So now, classically, how many queries would you need in order to decide if this function is constant or balanced?
n factorial.
Okay, so once again, what's your input? What's the number of input you have in here? 0, 1 to the, so you have a binary string, right? The length is n. So how many possible strings are out there? 2 to the n, right? So you have a 2 to the n inputs, right? So, n bits, right? So n bits. So this could be 0 or 1. So the possible input is 2 to the n, right? So if I ask you, if you want to determine if this function is constant or balanced, how many times you need to use this function? Probably, if you are not lucky, so what would be the worst case? You have to keep asking until more than half of them are all one number, then you know it must be constant, right?
Oh, 2 to the n minus 1.
2 to the n
Minus 1 minus
y minus 1 or plus 1. Or, oh no, you are saying the following. You are saying 2 to the n minus 1.
1. No, 2 to the n minus 1.
2 to the n.
Oh, 2 to the n over 2.
2 to the n, okay, oh, you're almost there. 2 to the n over 2.
Which is equal to 2 to the n minus 1.
Minus 1 or plus 1?
Plus 1.
+1, you're right. So if you are so unlucky, you'll just see half of them map to one number, but you don't know it's constant or balanced yet. You have to cross that border. You have the 2 to the n divided by 2 plus 1 to see it is constant or balanced. So classically, you need to do this many. So if n is large, you have to call this oracle, almost proportional to the 2 to the n, which is exponential, right? And quantumly, guess how many times you need to call?
Guessing n.
Okay, if I told you this exponential speed up, okay, so yeah, 1.
Oh, 1.
Only 1. So that will be kind of like saving you lots of computation, right? Okay, so what's happening here? So what's happening here is the following. You have a similar setting. However, for the input, you have to put, have extra qubits here, such that, okay, so if you look at the circuit, then you have the following, right? You have a fresh qubits, n of them, and the very last scratch paper is the same thing as what we did earlier. So it will be 0 to the n, and the 0 minus 1 divided by square of 2. Then you do the Hadamard operation, so definitely it looks like this, right? Each edge act on each 0, right? Okay, so that's what happened here, and then you clean it out a little bit. Actually, you can rewrite the first term in this format. So how do you get there? So the simple thing that you see is the following. So if you have a 0 plus 1, tensor 0 plus 1, what you're going to get is 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Okay, so obviously, if this is a 2 and this is a 2, you get the distribution from until 4, right? So the same idea sort of propagates. So if you have n qubit of those, you can definitely prepare the possible state from 0 until 2 to the n minus 1 by using the tensor product of the first qubit. Is that clear? Yes? Okay, so what does this mean? So now we are going to apply this UF we just talked about. So UF, we remember UF just take this term and put the minus sign in the front. You do the minus 1 f of x, right? If you recall what happened earlier. So remember this guy here. So UF acting on this, that would be the minus 1 f of x. Okay, so now before we go further, let us think about the next step is you have to apply bunches of Hadamard. It looks like getting a little bit hairier, right? Because you don't know what's going to happen. But are you still okay until here? From here to here, this is not a problem, right? So this here, and then you rewrite this guy to here because of the ULF. That's the property we just explained in the previous.
Okay.
Yeah. Okay. So now, let us look back on the Hadamard again. So what does Hadamard do? So look at this. Hadamard acting on x. X could be 0 or 1. We can simply write it like this way, right? So 0 plus minus 1 to the power of x. If x is 0, then you have a plus sign here, right? If x is 1, you have minus. That's exactly what we have here. So you can clean it up. So you just look at this. You have you turn those 0 and 1 into variables, right? So that you can simplify this form into this. Okay, so now make your life a little, expand a little bit. So what's going to happen now? If you have n Hadamard acting on those n qubits, and what's going to happen? You have the tensor product of everything in this form, right? So first Hadamard acting on the first x1, second Hadamard acting on the second x2. So obviously the result is the tensor product of those results, right? Okay, so this guy just directly go from here to here. Okay, so now actually if you write it up, so actually you can rewrite this expression in this form. So you just turn into this expression into this format. And here, what does xy mean? Here, just the bitwise operation. So for instance, if you have x is equal to 0, 1, 1, 1, 0, 1, and y is equal to 1, 0, 1, 1, 0, 0, then the x, y will be just the sum of these. So it will be pairwise. Okay, so yeah, so that should be straightforward, right? Okay, so now as you can see, you have n Hadamard acting on some particular x. The result can be expressed in this form. So that means let's refresh your memory. Say, the state before the last Hadamard. That's what we see, right? So that's the state we were talking about here, because we are going to encounter this Hadamard gate. But this is the state where we stop here, right? We want to figure out what Hadamard is going to do to us. So remember, that's the state before you encountering the Hadamard. But now we know the Hadamard and Hadamard are going to act on this x. X can be written out x1 until xn. So then you can say, if Hadamard act on this x, then actually I can rewrite this guy into this form, right? Based on the previous slide. Okay, so what I mean is the state before the measurement is this. 1 divided by 2n. And because, okay, so minus 1 f of x, minus 1 x, y. And x, y are, from 0 until 2 to the n minus 1. Okay, so here I just drop this term here because this is no longer important to us. So this would be the state, this guy would be the state right before this measurement. Okay, so what does that mean? So this is the state before the measurement. So if f is constant, the amplitude of 0, 0 is what? So let's say, let me ask you in another way. So if y is, so this y is all 0. So what does that mean in this expression? So do I have a eraser here? Okay. All right. So what that means is we have this form and the sum of the x, y, and then minus f of x minus 1 x, y, y. Right, so if this guy is all 0, then what you have is 2 to the n, sum of the x minus the f of x, 0, something like this, right? So what can that tell you if f of x is constant? That could be f of x is always 0 or always 1. So if always 0, then you have a 2 to the n sum over the 2 to the n of the 0, right? Because x goes from the 0 to the 2 to the n minus 1. But if it's a 1, so what you got here is 2 to the n minus 2 to the n 0. So what that means is if your function is constant, okay, so what that says, if you observe a 0, that means your function must be constant. So let's say if your function is balanced, so what does that mean? So what's the probability of seeing a 0? That is because half of them go to 0, half of them go to 1, so they'll cancel out each other, right? So that means the 0 probability of observing y. So what that means is the following. When you measure here, if you see a 0, all 0 here, then I know this function f must be constant. If I observe any value other than 0, I know this function must be balanced. Okay, so as you can see, of course there are some sort of computation here, but I'm just trying to let you see that how people play with the property and show that you can use one quantum gate, then you can decide if this function is a constant or balance. So here's the exponential speed up in comparison to 2 to the n divided by 2 plus 1.
Can you explain, so when, I don't see why, when it's balanced, why is the probability 0 getting zeros?
Okay, this one you don't see it. This one you see it.
Alright, that's okay, yeah.
Okay, so let me expand here. So if f of x is balanced, so that means half of the x must go to 0, half of the x go to the 1. So here the x is from 0, 0, 0 n bits until 1, 1, 1, 1, so n bits. So somehow half of them will map to 0, half of them map to 1. So let's say if x is, let's say they computed half of it, they are mapped to 0. So what you're going to have is half of n, okay, sorry here, times, okay, sum of x is that the f of x equal to 0, minus 1 f of x, 0, 0, plus half of n, sum of x is in the set, the f of x is equal to 1, right?
Oh,
so this guy got the 1, this guy got the minus 1, so they have an equal number of quantity, and 2 to the n divided by 2. So the sum of them will equal to 0. So that means there's no probability you can see 0. Right? Okay, so in other words, if you observe anything other than 0, then you know this function is balanced. So you only use one call of the oracle, then you are done. So this is exponential speed up from 2 to the n divided by 2 plus 1 goes to just 1. So here's the promises that look like you are asking the query in parallel, right? Just using the quantum gate. So that's why I say, well, it looks nice. So here's okay, so here's what I explained here, plus 1. And here's the probability is 0 because there's no chance you can observe it's a 0, then it's a balanced function. Okay, so that would be for the first part of this. So any question on the Deutsch algorithm and the Deutsch algorithm?
So one of the assumptions is that these gates, if you go back, has to be symmetrical, reversible.
Yeah, so quantum gates, they are always reversible because of the time evolution is reversible.
Put it that way,
Yeah.
it should be able to get back.
Yeah. Okay, so any other question on this? Okay, so I should continue with the next one. Next one is a little more interesting. Okay, so the next one is quantum walk. Okay, so this is the some of the maybe 20 years ago people say let's have a quantum computer, and some people come up with the this exponential speed up kind of problem. Say okay, obviously here's a selling point. Right? Here's a selling point. If you have such a problem, then I can have exponential speed up using the simple Deutsch algorithm. So for the past 10 years, people come up with some other more interesting algorithms. For instance, okay, so now let's look into the quantum walk. Before we start with the quantum walk, let me talk about what we covered in this section. So here we'll talk about random walk and quantum walk from 1D to graph. And the next one is how do you quantize a random walk into a quantum walk. And then how do you obtain the spectral theorem by using the phase estimation on the quantum walk. Okay, so here are three parts. First thing is, okay, let's ask you something very simple. So what's the walking on the line? So let's say if you are starting from 0 and you have a probability of 50 going to the right and probability of 50 going to the left, so then the question would be, okay, so this is like a random walk, right? On the line, you can go left, go right, probability 50-50, right? Okay, so now let's say each location have 50-50 turning left or right, and what's the probability you will be at location X at time t? Right, so this is probably can be easily solved. Okay, so what does that mean here? Okay, so well maybe I didn't go into those details. Just take it as it is, because you can see, you know, you definitely have a. Okay, so maybe I just grab this, right? So let's say you have a y to the right. Okay, so x to the right, and the y step to the left. Okay, to s prime. So you must know s prime plus y have to be equal to x. How many steps you turn left and how many steps you turn? Okay, so I should be more careful. So your right is this, right? Yeah, so that's fine. So your x prime plus y must be equal x. This here is to the left y times, right? And to the x at the plus location s prime times.
Y is a negative number?
Y is a negative number. Yes, y is a negative number. Okay, so and then you have an x prime plus the absolute value must be equal to t, right? So obviously you can cut this s prime could be x plus some y, such that this y cancel this y, right? No, yes? And then that's why at the end of that you end up with x. So that's why you derive this value, right? So t plus x divided by 2. Okay, so this is easy. So as you can see, this is a simple random walk on a line with a probability 50 and 50. Okay, so
Can you explain the notation? What's the notation?
oh, this is notation here. Okay, so
Does it have?
okay, so I'm sorry, there's no hand. Actually, let me. I didn't realize. Okay, so here here's a t time step that definitely have a 2 to the t possible condition, right? And only this many combination will take you to the x. So that's the computation here. Okay, so now it's clear. Okay, so now here you want to extend this random walk on the line into the Pontiff Walk. Right. So here is the same thing. So you have a two register, X and C. So X is the register that holds the position, and C is the coin register. So it tells you go left or go right. So now you have a fundamental data structure holding where your position is, and you are facing left or right. And then definitely you have the move operator, right? So you have to move using this operator S, and the coin operator says up is left or right. Okay, so what's happening? Let us turn this coin operator as a harama as again. So if I see you are facing left, then the probability will be had that 1/2 square root half that you will be turning left or right. Or you can do the following. So you have a coin operator. If you are facing right, you could be the next move. You could be either left or right, but the coefficient of the right will be negative. This is just like the Hadamard transformation, right? You can think of the L as a 0 and R as a 1. Right? So maybe it's easier we look at the example. So let us initialize the state location at 0 facing left. Okay, so this is initial condition. You are starting with the location 0. You are facing left. Similar to the very beginning, right? You are starting at the location 0, then you just go left or go right. The drum man left and right? Okay, so if we simply look at this operation, you could run this for t times. That's where you are at the end of the day. So it will be s times I tensor z to the power t, 0 and L. So what does this mean exactly? So look at this one. So let's say you're starting with 0 and L. So then you have decide flip the coin. So you flip the coin and then you move, right? So if you do the flip the coin, what's going to happen is you're gonna turn into left and right, left plus right. And then this move operator will decide to move left or move right. So in this case, because you move left, because you have the coin operator decided to come left and right, and then definitely from here, you see a left, so you move to the left by 1, so your position is -1. And here you see the right, so from the 0, you move to the right, so your position is at 1. So quantum-wise, you could be, have this kind of distribution. So if you do a little bit more, you have those properties. So let's assume the computation are correct. Okay, so actually they are correct. So what's going to happen is that this is the result. So if the red line, that's the classical random walk. It looks like you will be centered around the 0. This is you just a drunk man, left and right, left and right. Quite likely you go back to the 0. This is a distribution. However, quantum-wise, you could be more sparse, more spread. So what does that mean exactly? So if you are starting from some place, and there's a place far away you want to get to, by intuition, which walk would you use? Quantum walk, because if you use a random walk, quite likely you are just staying where you start, 50%, 50%. But if you have no idea what's going on, use a Hadama flat coin and use a quantum walk, definitely more likely you enter the further places. You can reach the place that you want to go to, right? There's some place that's far away you want to go. So quite likely you use the quantum walk, right?
One thing, this reminds me of Feynman's double slit experiment.
Okay, so what's that?
Remember?
No, what's that one?
So if you have a single slit, okay,
Uh-huh.
we're going to get the interference pattern,
Uh-huh.
Young's interference center there.
Uh-huh.
If you have a double slit, you're going to get that thing.
Maybe the double slit have causing the quantum effect or something.
Exactly.
So there's some analogy, right? Yeah. Okay.
But I have a question. What determines the pipe, the place of the pipe?
No, you just run a simulation. You run that 100 times. So you have a distribution, right? So for instance, after 3 time steps, that's where things are, right? So you have a location -3, location -1, location 1 and 3, right? So this amplitude here will be deciding your probability. So if you run that,
If you run more, you just go.
yeah, it gets bigger, right? So it gets bigger, and it turns out, it's more likely you can reach a higher, amplitude at the far end. Okay, so obviously, if you have some place that's far further away, you want to reach, don't know, then maybe it's a quantum walk. It's an idea, right? So here's a quantum walk on a line. So that's simple, right? So you definitely just this one, beginning from walk on the line from the classical random walk, and then you can sort of say, now I use a quantum walk. You have the position register, and you have the coin operator. Have the coin register, and coin register is controlled by the coin operator, and the location is controlled by the move operator. But move operator reads the result from the coin, right? So that's how the walk takes place. And here they have this interesting property of the distribution. Okay, so now how do you work on the graph? So how do you work on the graph? So now we know how to do it from 1D, from one line, in a quantum walk on one line, or in a random walk on one line. Now how do we work on the graph? So let's say you are given a graph, and graph is have amped vertices, and you don't know. Okay, so let's say you don't know about how many edges you have. So make your life easier. Maybe you can consider undirected deregular graph. So what's a deregular graph? Deregular graph, if you know, have D neighbors, right? So that's a deregular graph. And let's say each way in each edge is the same. Okay, so now, if I ask you a simple question, so if you random walk on the graph, so let's say you're starting from location I, and you have a stochastic transition matrix M, then what's the probability finding you are at location J after time t? So it's quite simple, right? So it's most likely you have the transition, and you are acting starting from the location J, I, then you run it t times, right? And you want to find out at the end of the day where you are ending up at the J, right? So if you play with the matrix a lot, you should know this is what's happening, right? So for instance, let me run the simple scenario. So let's say you have a simple matrix like the following. So let's say you only have 1 and 2. So this is not a good one. So 3. So the matrix is getting bigger. It's getting harder to compute. So let's say here you have a A11 until A33. Now so here you have A21, so on and so forth, right? So this is your M. So if I do this, acting on this guy, so let's say M 2 times onto, let's say I start from position 2. What's going to happen? So probably you just choose this column here, right? So what's going to happen is you have a M acting on the A12, A22 until, okay, so A32, right? And then you do it again on this. Then it's getting a little more complicated, but at the end of the day, you get another matrix. So you want to figure out if it's at this location J, you just see up, what's the probability it gets there? Right?
Like Markov chain.
Yeah, it's just Markov chain. This is just simple Markov chain. So I'm just trying to tell you. So if you have a Markov chain, then after time t, what's the probability you are ending up with J given you are starting with I? So this is the probability that where you end up with. And here they make your life easy because let's say Mij is equal to 1 over D. That's because we assume it's a deregular, right? So it's a deregular graph, and if I is connected to J, and Ij is 0 if because it's not connected, right? So here just telling you the structure of the M, and here's the probability of getting to state J after time t starting from state I. So this is walking on the graph using a random walk. Right? So is that clear on this? Okay, so now you say, okay, so I'm a little bit confused on the random walk on the graph, so I'm gonna quantize it. So remember from what you learned earlier, you want to quantize it. Then what do you need to have? You might have a location operator and the coin flip operator, right? And we talk about the quantum walk. We have 2 parts, right? The location and the coin. So as you can see, if you label the vertices from 1 through n, and you have the edges 1 through d, then let's define the S operator. That's the one that tells you, move left or move right? So here, let's say, SVI is that you move to the ith neighbor of vertex V. Okay, so let's say remember earlier you have this location and the coin, right? But who's acting on them? Who's acting on them? You have this X, the mover, but first of all, you have to flip the coin first, then you move, right? You make the coin, you flip the coin first, decide if left or right, and then from left or right, you will move your position, right? Right. Okay. So obviously you can see if this is a quantum, that means simultaneously you also have, let's say, how do you say, simultaneously obtain all of your neighbors, unlike the classical ones. Okay, so let's not worry about the detail. Just think about, you have a general idea how to quantize a random walk. Okay, so here they have this idea, say, well, you have this Grover operation, that would be good for using this the coin operator here. That's a good choice. So obviously, in real life, you really have to quantize whatever stochastic matrix that's given to you. Now here we always assume, not symmetry, uniform, 1 over D, that kind of property, but obviously you can't. In real life, you have to quantize, whatever is given to you. So you still, maybe at this moment, you still have some big question marks, say, what's going on? So let us look into the mathematical expression. Maybe that's more clear to you. So look at this, classical walk operator. You have this Markov operator, the stochastic matrix. This is a column-wise stochastic. Right? This is a Markov. So what's the quantum walk operator? How do you quantize it? First of all, I know the quantum walk operator is WP is 2 steps of a unitary. And how is the unitary obtained? This unitary is obtained through this quantization of this P. Okay, so you have a transition matrix. Classically, you want to quantize it. And how do you quantize it? That will be something explained later. However, even though this U, 2-step of this U is based on this P. So we're going to talk about how it's quantized. Okay, so here it gets a little bit hairier. So here what I say is this U operator is actually a swap operation times the 2 pi minus I. I is the identity. So what's this pi? So pi is all the collection of the psi s, the outer product of psi s. And what's a psi s? Psi s is just a distribution. For instance, look at here. So if psi s, look at it. So location x, then you have this v acting on it. Then you have all the probability that where x can go to. So if you look at this example, so for instance, let's say this is your location, and here's the places you can go to. So after applying v, then definitely you have the square root of p1 and square root of p3. So what's happening here? You come back to look at this guy. So here's a 1, here's a location 0, here's location 1. So if you do that v operation, that means just if you, okay, so let me write this. So if you have the p, it's equal to p1, p3, p2, p4. So if you use this notation, the probability of 0 go to 0 is p1, 0 go to 1 is p3. If you apply with the math. So that's the state 1 can go to 0 with the probability p2 and so on and so forth. So now let's look at the U operator, because we need to quantize this P to get to U, and 2-step of U will be my walk operator, right? But you look at the fundamental best building block of the U is a swap operation, which is easy. But the next one is a difficult one, is this pi operator. And how is the pi operator obtained? It's the sum of the outer product of psi x. And what's this psi x? Psi x just the following, right? So psi x is that from all the possible state space, x, maybe from 0 until the psi state space, and then you say where they can go to. So obviously, if you look at this guy, look at this example here, V00 would be definitely square root of P00 plus square root P3 over 0, 1, right? Because this what it means in this term is the probability moving from state X to the ith neighbor of X. So this is the first neighbor, and this is a second neighbor, right? Okay, so that's what happened here. Okay, so questions?
So you don't know which compare with this classical random walk. So which one become become different? You can see because this random walk there are two parts, right? One is the point you see decide you.
Okay, so I know where you're going. So this leads to the final spectrum theorem. Okay, so maybe I'm talking about how to construct this walk operator, right? So we have to talk about how to construct this walk operator. Let's assume you know, okay, this is how the walk operator is constructed. Okay, so now, so this is a walk operator, right? You have original, let's say the Markov, you have given the Markov, and then you somehow do some modification on this original Markov. And why we do that? We'll explain that very shortly. And based on this, you can derive this discriminant matrix. And from discriminant matrix, you have something to do with this unitary, because this discriminant matrix D has some eigenvalue lambda x, and D has something to do with the eigenvalue of U as well. And these two eigenvalues leads to the spectrum theorem of the quantum walk. Okay,
So I think what he's asking, correct me if I'm wrong, I can see location as a classical correspondence, okay? Coin has no classical correspondence as such. Coin toss. Is that what you're after?
Right.
So what would be the classical correspondence to that? So for instance, I could say location and momentum both together could be used as a construction for unitary matrices. Are you going in that direction?
No, we are given the assumption that we are given the transition matrix, and we work on the transition matrix. Is that?
Yeah, I'm still trying. I'm a classical man. I don't know anything about quantum mechanics. So I'm asking myself, what are the classical correspondences I'm relating to?
Okay, so you're saying correspond?
Here I'm located. Now I'm going to move. I'm facing that way, or I will be facing that way. I'm going to toss, and that toss itself will determine how I'm going to move. With not the probability, the amplitude of the probability. Okay? That's where your U comes in. Now the question is, I'm still trying to think desperately, what is that experience, classical experience, I could relate to?
Okay, in real life.
Real life.
Okay, in real life. Okay, so what?
Or there is nothing.
It's a quantum coin.
Huh?
It's a quantum coin.
Yeah, well, don't just shove it as a quantum point. I'm just trying to.
Okay, so this is something you can do. So let's say if you do the speech recognition, so definitely they have a transition matrix. Say, given this phrase, what's the probability the next word would be? So that would be.
I can understand probability already.
Yeah.
What I cannot understand is square root of probability.
A square root of probability.
That's the problem.
Okay, so that's the difficult part, because that guy who got the prize, Nobel Prize, he said that's how he observed the square root sum of the square of the square root of the amplitude square sum up to 1. That's the I don't know, quantum mechanics property that we follow.
Oh, all right, okay.
Okay.
That's hiding under the carpet.
Yeah. Okay. But another way to say is because I'm not a physics person. I'm from CS, so I'm taking the quantum mechanical properties and to play with them and see how things goes.
I'm thinking it from physics point of view.
Yeah. So that would be good, right? So maybe we have some physics, and maybe we can talk about this more. Okay. So now the next thing is, okay. So before we talk about those details, there are a couple of things, right? So you have a graph, and let's say some elements inside the graph, they are marked, and you want to find them. Okay. So task is that how fast the random walk can get there, and how fast the quantum walk can get there, right? Okay. So from what we said earlier. Okay, so the intuition I was introducing earlier when we are walking on a line is that obviously quantum walk can get to the further place faster. But now we are trying to show how fast it is in comparison to the classical walk. So here's the property. I know it's fast, but how fast? So here's the property, right? Okay, so let's say you have different original vectors P. Then you need to modify it to T tilde. And why do we do this? Let's say your mark state is in this region. So once you get to the mark region, you definitely want to stay there, don't move anymore. Otherwise you walk away, right? So if you modify your original transition matrix from P to P tilde, then based on, if you use in this P tilde, if you start a classical random walk from the uniform distribution of mark elements, how fast you can reach the mark element is 1 divided by 1 minus the first norm of PM. So this is some complicated proof. Let's take it as the fact. So maybe like a couple pages proof, but you just say, okay, so I know this. Classically, the time takes for me to reach from non-solution or non-target state to the target state is 1 divided by 1 minus PM, the norm of it. Then there's this lemma by Segedi. He say, well, if the second largest eigenvalue of P, which is this P tilde here, is almost 1 minus delta, and M is less than epsilon n. So what it is trying to say is the number of elements in this mark region is only counting epsilon fraction of the total n here. So what is the is the following? P, PM, 0, 1, 2. This is n by n. And the PM itself is n minus m times n minus m. So here, this is n, and this region is m. So this is the mark element area. Okay, so let's say, well, then they can find out how big PM is. So given this second dilemma, it already tells you the hitting time of the classical walk is 1 divided by delta epsilon. Okay.
Why second largest value? Eigenvalue.
What's the second?
Why second? Why not first?
That's called the spectral gap.
Okay.
So how the Markov chain converges is corresponding to the spectral gap. This is the property. If you have a Markov chain and how fast you from the uniform distribution to the stationary distribution, how many times you need to operate this Markov chain is proportional to 1 divided by the spectral gap.
So we're talking about first passage time from one state to another in Markov chain.
What do you mean by the first passage time?
Because remember, Markov chain is basically memoryless. Okay? So if I'm starting at a particular state and randomly walk, eventually I would go visit that state many times. So about what is the first time?
So you are right. Hitting time is the first time you hit the place you want to go.
Yeah.
Correct. So that's a definition of hitting time. Yes. Okay, so classically, this is how long it will take for you to hit the target. All right, so maybe I should just talk about the property here is that if remember the U operator we try to construct from the classical one. If you remember this guy here, you construct the U. So there's some property with this U. The property with this U is the following. He has the corresponding eigenvalue plus minus 1 e to the I cosine lambda I. And what is this lambda I? This lambda I is the eigenvalue of the discriminant matrix D. And how is this discriminant matrix D is constructed? It's constructed on this P tilde. So as you can see, if your P looks like this, P tilde looks like this, then your D will look like this. Then the eigenvalue of the U will have this correspondence between this with this discriminant matrix D. Okay, so where are we going with this? So let me simply skip those technical part. What I'm trying to say is, at the end of the day, if you use the Pontiff Walk, quantize the operator, then your heating time actually square root speed up. So that will be the result of it. But there are lots of, this is like 5 or 6 lectures of proof. So I'll just let you know the result. So Pontiff Walk, if you construct the corresponding walk U, based on the technique we just said, and if you look at the proof, and then say, well, you definitely have a speed up in comparison to the classical one. And the speed up is a square root speed up. Okay, so this is just a message. So here is something people have done, and this is just a walk operator. Okay, so now the third one is using the spectral probe to set problem. Okay, so any question on the because I think the Pontiff Walk itself is kind of hairy, so it has lots of details that I just give you the results, but take it as there are some people already shown that it's correct. So that's the idea that's saying, okay, so you can construct the Pontiff Walk, and definitely its performance is better than the classical ones.
Is that a well-known result, the theorem you just presented?
Yeah, it's a well-known result. Okay, the third one is something that I read recently. I think it's more interesting. Okay, so this has something to do with the people from physics. Okay, so for this one, what I'm trying to do here is that how do I use a so-called spectrum probing approach to solve a set problem? Okay, so first of all, I'll talk about what's a K-set and what's a Jens-Cumming or Talbot-Cumming model. And then I'll talk about how you use a spectral probe to solve a set problem. And then I'll talk about the possible improvement. Okay, so this is something I'm writing recently, and hopefully it works. Okay, so let's see the following. So what's a set problem? So set problem is the following. So let's say you have a variable, n variable, right? So we have a v1, v2, and a vn. That be the set of the Boolean variable. So that could be 0 or 1. And let's say v tilde is just a negation of this variable. So if v1 is 1, the negation of the v1 must be 0, right? So if I give you a formula f, c1, c2, c3 until cn, that means it is a formula with the n clauses. And each clause can be written in terms of this is a 3-set, right? So each clause has the 3 variables. We'll call that literal there. It's not variable because literal could be the complement or the non-complement part of the variables. So that's the way we say, okay, I'll give you a 3-set problem. So it's f, and then we have n clauses, and each clause has a 3 literal. Each literal could be the variable itself, v1 through vn, or each literal could be the negation of the variable. So the question is, how do you find assignment, of v1 and v2 until vn, such that you can find, such that f will be evaluated to 1. This is so-called, the 3-set problem. It has been shown that 3-set problem itself is NP-complete. So that means lots of NP problems, that can be converted into this. So if you can solve this, you can solve the NP problem, right? But if you can solve this easily in the polynomial time, so what does that mean? that means you got $1 million. Because if you can show P equal to NP, then you got $1 million. Okay, so now,
A lot more mystery.
okay, so now, as you can see, here are the assignments, right? So here are the assignments. So here I just try to say again. So all the literal must be either variable or the negation of the variable, and those numbers v1 until vn must appear at least once in this formula. If it does not appear, then you cannot call it, n variable, maybe n minus 1 variable. So that's the case. So now what I'm interested in doing is, because in their paper they are physicists, so they just give you a general situation. So they did not tell you, what's really happening. So what my take on that is that, actually really hard instances is depend on the clause variable ratio. So there's some papers show that, if you have tons of clauses and very few variables, it's quite likely you cannot find a solution because it gets rejected easily. And if you have very few clauses, that means you have lots of solutions, right? So people show that for K-set problem, the difficulty of K-set problem is coming from the ratio here. And for the 3-set, the ratio is about 4.24.
Oh, interesting.
So I think if you later look at the reference, there's a couple papers about this. Okay, so now my target is, hey, I want to look at those cases that are hard for the 3-set. That means I have n variable, I have 4.24 n clauses. Those are my target I want to attack, right? Okay, so the first thing is that that paper, what they use is they use the Jens-Cumming model. You say, if you have a 2-level atom with a frequency omega 0, interact with the quantized mode of a cavity, all right, which have a frequency omega c. Okay, so when the frequency of the 2 levels atom is close to the frequency of the cavity, then they can interact. So they have this Hamiltonian for the whole system as the following. So here the Hamiltonian of the P is this the probe in the atom itself. HS is this Hamiltonian of the cavity. And this Hamiltonian interaction is how the cavity interact with the atom. So based on the Jens-Cumming model, you have this corresponding Hamiltonian. So here that means, okay, so here I just wrote out the expression. However, I just try to say in the more, generalized way, I put out the T there, because if T equal to 1, then it's JC-Cumming model. If T equal to greater than 2, that will be the Thomas-Cumming model. Okay, so if you look at this, what does it mean here? So it looks like, if you look at this S minus A plus or S plus A, that means it looks like this X is acting on the probing atom. So that means atom, if it's minus, okay, it's a minus, that means you are going from excited state to ground state, right? They're going from excited to ground, but here A is increasing, that means A is going from the ground to excite. So you also are doing the energy exchange. So this is the interaction of the Hamiltonian. Okay, and what about this S plus minus? Okay, so what's this guy here? Okay, so this XZ. So XZ here is definitely just describing the behavior of your atoms, right? So it's just like a sigma z operator. It's simply just a sigma z operator if t is just equal to 1. So obviously, extending from the JC-Cumming model, then you definitely here you have this some h constant there. You can set it to 1. So obviously, you can rewrite this complicated Hamiltonian into this way. So here is the Hamiltonian of the atom, Hamiltonian of the system, and Hamiltonian of the interaction. So they sort of compute that, well, how the energy from the the atom can be sent to excite particular state in the cavity to another state J. So what they are counting here is the following. So maybe I shouldn't explain the detail, just take it as it is. So how the probability you get the zero, suppose you are from the probing state from excited, how you get to zero must be I have so much energy, but those cavities stole from me, right? The cavities stole from me. How they take the energy is the following, right? So how they contribute to my getting a zero is the following. It's such a gigantic expression. However, here you have the several terms. Right here, here's a Qij or omega ij. So what's a Qij? Qij is just the overlap of the I and j's eigenvector of the cavity being interacted by the interaction Hamiltonian. Okay, so maybe we should. Then the next question you ask is, okay, so how is this related to the three-step problem, right? So how is it related to the three-step problem? So here's the interesting part. So that's how they did it. Say they construct the corresponding Hamiltonian for the system, the cavity, in the following way. First of all, they define HC. So what's HC? So that's the Hamiltonian acting on the input and tell you it satisfies a particular clause or not. So if you have n clause, then definitely you have a HC1 until HCm. So then, at the end of the day, you sum up those possible, HC1 until HCm, that would be your corresponding HC. So now you can see that the cavity Hamiltonian they construct in this way that it's the upper left is a minus identity operator. Okay, identity, and the lower is just the Hamiltonian of those HCIs. Okay, so you say, well, what is this doing here, right? Okay, so let's say if you have prepared initial state, that's the following. So I2 times H to the n, and then you prepare the I would say superposition. So what does that mean here? This guy is definitely an eigenvector of this HS, right? Because here is identity. No matter what, you have the first bit is 0. Definitely, you are the eigenvector of this Hamiltonian HS with eigenvalue -1. Okay, so had that been the case? Had that been the case, then it also defines what the A operator is. So here's actually the circuit. What's happening here is you define your gigantic Hamiltonian, which is equal to HS plus HP plus HC. Plus H interactive. So if you let it, if you base it on the gigantic H, then you can run this gigantic U, and here's a simple setting. So the setting itself is very simple. So at the end of it, you just measure. If you get a 0, it's quite likely you get the answer already. So you say, I really don't know what you are doing. So let me do it more like this way. So let me ask you the following. Okay, so if I know I have the assignment m variables. So how many possible assignments do I have? 2 to the n, right? 2 to the n. Okay, so think about this gigantic HC is a 2 to the n by 2 to the n matrix. Then what's going to happen is the following, right? So you have the following. You have a 0, 0, 0 until 1, 1, 1, 1. Right? And then what do you have in the HC? HC is the sum of the HCI. And I is equal to 1 until n. So what would happen if you HC, this gigantic HC, acting on an assignment? You spit out how many clauses this assignment violates, right? Because if you go back to the slide here, see this one here. So here is telling you, okay, if you violate this particular clause, ith clause, I give you a 1. But now I have m clauses. So if I test all those m sub Hamiltonian on you, that means I'll be asking how many clauses you violate, right? Okay, so obviously you can see here 0, 0, 0, 0, 1, 1, 1. So probably it's a diagonal matrix, and here the value are just number of the clauses you violate.